Welcome back. This is lecture 35. So up until now we have been discussing different topologies of amplifiers using single transistors, multiple transistors. Then we graduated to differential amplifiers. We saw multiple topologies of differential amplifiers also, and we now know that the reason we are doing all these things is because we have to put things in negative feedback, right? Before we proceed with the consequences of putting things in negative feedback, let's focus on something that we have been avoiding till now. So if you might have noticed that we kind of have avoided the capacitances associated with the MOSFET, right? The reason I am saying we have avoided the capacitance with associated with the MOSFET is because we have treated the MOSFET as a voltage controlled current source, right, with some resistance at the output. That was the basic treatment of the MOSFET. Yes, we had put capacitors at different places in order to couple the signals and make them AC shorted and so on, right? But those are intended capacitances that we had used for our use. However, we know that. However, you know that what is a MOSFET? By its very definition, a MOSFET is a metal oxide semiconductor, right? So your MOSFET, if this is a p-type substrate, on top of that p-type substrate we had an oxide layer, and on top of that oxide layer we had a metal layer, and obviously here we have N plus, right? So this is metal, this is gate, here this is oxide, and here we have, we can connect this, call this drain, we can call this source, right? And we have another terminal which is body, right? Let's do the other way around. Let's say this is drain, the other one is source. So this is drain, this is source. Let's call this body, and we kind of have assumed that source and bodies are tied together, and when we did our analysis, we assumed that they are all grounded. That's fine, but in all our analysis, what have we done? We have essentially said that when the transistor is on, then we have, this is the NMOS transistor, so we have a battery VGS. We apply a battery of value VGS, right? And what does it do? It essentially creates a sea of electrons here, right? It creates a sea of electrons. So this is a sea of electrons. That is something that we call a channel, right? Provided, obviously, the way I have drawn it, it is assumed that VDS is almost equal to 0. This is under the assumption that VDS is almost equal to 0, right? So in other words, the transistor is in deep linear region. Okay, so if that is the case, what is going to happen, right? So let me just say that we have electrons here. So what is going to happen? Okay, so let me short these two also, right, just for sake of clarity, right? So what is going to happen if now I change the gate to source voltage, right? What is going to happen? So this is a capacitor, essentially in your MOSFET. This is a capacitor, right? So this is gate and this is the channel. This is the channel. So essentially we can think of this as a distributed capacitance between the gate and the channel, correct? So essentially we have capacitance between the gate and the channel, and also you have this source and drain contacts on either side, right? You also have source and drain contacts on either side. So this is the distributed capacitance. and you have channel charge here. So if you change the gate to source voltage, you are able to change the channel charge, right? So what is the value of this capacitance? What is the value of this capacitance? Note that this capacitance, whatever we have done, right, your IDS, in the IDS equation, in linear region, the current expression is mu n Cox W by L, then VGS minus V threshold voltage times VDS minus half VDS squared. What is this Cox? This Cox is capacitance per unit area. Which area? Is the area of the total area of the gate, right? So if I sketch the gate area, right? So if I sketch the gate area properly, this is what it will look like. So on if I make it like a three-dimensional structure, so essentially this is what it looks like. We have seen this structure before when we introduced the MOSFET, right? So you can assume that this is drain and there is a source contact somewhere there. There is a gate contact somewhere there. And what is L? This is L. And what is W? This is W. Right? So if that is the case, what is the total area of this entire plate? Total area is W times L. So under linear region, so in linear region, when the channel charge is uniformly distributed, the total capacitance between gate and channel will be what? Will be equal to Cox times W times L. Cox was the unit area, capacitance per unit area. We simply multiply by the area and we get the total capacitance, right? But note that the issue here is that even though we can define this capacitance between the gate and the channel is not accessible to the designer, right? However, what is accessible? The source and the drain contacts are accessible. So if I can express the capacitance between the gate and the source and the gate and the drain, then it will make our life easier, right? It will make the capacitance will be useful to a designer. So what we generally tend to do is to say that we understand there is a channel charge. We understand that there is a channel charge, right? But we also understand that this channel charge will ultimately get influenced by the terminal voltages, right? By the gate, source and drain terminal voltages. So what we tend to do is to say that we will split this capacitance into two parts. Because this is like a uniform charge distribution, we will split the capacitance between two parts, and we will say that half the capacitance will apportion towards between the gate and the source side, and half the capacitance will apportion between the gate and the drain side. So essentially what we are saying is, instead of assuming the capacitance exists between gate and the channel, we will say that the capacitance exists between gate and the source and gate and the drain. Okay, and we'll say that this gate and between the gate and each of them are identical, because there is no way to distinguish a rectangular slab of charge whether it is more towards the source or more towards the drain. So we'll just simply say that CGS will be equal to Cox times WL by 2, right? And between the gate and the drain it also will be Cox times WL by, right? So in linear region, so your CGS becomes Cox times W times L by 2, and CGD also becomes Cox times W times L by 2. Okay, fine. But this is also not enough, because what you will notice, if you look carefully, you will notice that there is certain amount of overlap in this, around this junction, right? There is certain amount of overlap between the physical overlap between the oxide and the N plus region, right? There's a certain amount of physical overlap, and that has to be there, because if that overlap is not there, your channel, there will be a region where the channel cannot be formed, right? Both towards the drain and the source side, and your transistor action will be lost, right? So there has to be an overlap, but because of that overlap, there will be a physical capacitance and extra capacitance also associated between the, use a different color, between the gate and the drain, and on the other side also between the gate and the source, right? But this capacitance, right? So similarly, we'll have we'll have a plus C overlap capacitance on both sides, right? Now, just like Cox is expressed in terms of capacitance per unit area, C overlap is expressed as capacitance per unit length, because how does the C overlap change? Does C overlap get changed with respect to length? If I increase the length of the transistor and don't increase the width, will this overlap capacitance change? Clearly not, right? Because ultimately it looks like if I increase the width of that transistor, if I go this way, then I will have more overlap capacitance. And however, if I even change the length L, the overlap capacitance will not change, right? So essentially, which essentially means that this C overlap, or we express this as CGS overlap. So this CGS overlap is often expressed in terms of per unit length, right? So we'll call it CGS overlap times L, per unit width times W. And similarly, CGD overlap will also be expressed in terms of per unit length, per unit W. So this will be CGD overlap times W. Note that this overlap capacitance will be same towards the gate and towards the source and the drain side, but just that we are used to using different terminologies, so we use, right? So to quickly recap, CGS, so CGS overlap unit is farad, or capacitance per unit length, and Cox, the unit is capacitance per unit area. Okay, so why is this critical? This is critical because we need to know this, because for some reason, let's say we double both the width and the length of the transistor, right? So if W and L increases by, let's say, alpha times, then what will happen to CGS cap? What will happen to CGS? So in this case, CGS will increase by approximately by So before I proceed, I should also I should also make a comment that this capacity, instead of saying CTS capacitance, let me call this channel capacitance, right? So this is a channel capacitance, and this is the other one, the overlap capacitance, right? So if we say this, then we can say that the channel capacitance increases by alpha squared, and the overlap capacitance increases by alpha. So they don't scale similarly. So this can have design impact, right? Okay, fine. That is something that is good to know. But another interesting thing that happens is, what happens when our transistor is in saturation region, right? So this is kind of triode region operation that we are dealing with. But let's say our transistor is in saturation region, then what happens? So let's see. So in saturation region, let me get rid of this stuff. What changes? So what changes during saturation region? During saturation region, we have a battery anywhere between gate and the source, but the drain is at a higher voltage than source, right? Because pinch off and all, right? So when pinch off happens, what changes? When pinch off happens, the channel charge distribution changes, right? So the channel charge distribution changes, and what does it look like then? The channel charge distribution essentially then at pinch off looks like something like this, right? So you have, so this is the electron concentration, right? And what happens at that drain channel junction? At the drain channel junction, there is essentially no channel, right? We have pinch off. So if that happens, right? So this is, let's say, at saturation. We have something between the drain and the source also. Otherwise, saturation condition will not be ascertained. So at saturation, we cannot influence channel charge from drain because of pinch off, correct? So which means that the entire charge now, if I change the gate to drain voltage, this channel charge is not going to change, right? So which essentially means that all the influence, right? All the influence is now between the all the influence of changing the channel charge falls on the shoulders of gate to source, right? So, but we can still change channel charge from source, right? So another effect of this we saw earlier, the impedance looking into the source is low, right? Because we can change the channel charge and hence change the current, but the impedance looking into the drain is high because we cannot essentially change the channel charge, we cannot change the current, right? So that was another manifestation of that. I mean, similar things can be argued in terms of channel charge, in terms of capacitance. We cannot change anything since we cannot change the channel charge by moving the drain voltage. So, I mean, if we only move the gate to drain voltage and keep the gate to source voltage constant, then we'll essentially not be able to change the channel charge, right? So, however, the channel charge can still be influenced by changing the gate to source voltage, which means the entire channel charge, which was initially equally split, right? The entire capacitance that was initially split between the gate and the source and the gate and the drain is now shifted towards the gate and the source, right? So, which means that, which implies entire channel capacitance shifts towards CGS. And what is CGS now? CGS is again Cox times WL, but not by 2 and not also Cox times WL. It's apparently, as it turns out, it's 2/3, because I will not get into the derivation why it's 2/3. You can look up in a device textbook, but the intuition is the area of this channel charge, right? The area of the channel charge has reduced, and if you talk about the center of gravity of the channel charge, right, then you can say that it's like 2/3 towards one side than the other, right? So since the total charge has also reduced, so we assume that the capacitance has also reduced, and then essentially CGS becomes 2/3 Cox times W by L. So this is the 2/3 Cox times W by L. This is the channel charge, right? However, the overlap capacitance still exists, because that is a physical capacitance, because it was a physical overlap between the gate and the drain. So which means that I still have that overlap capacitance. So this will be CGS overlap times W. And what is CGD now? CGD becomes, we don't have any diffusion capacitance, so diffusion capacitance goes to 0, right? So essentially this becomes 0 plus whatever we had, CGD overlap times W, right? Okay, so as it turns out, generally the channel capacitance is much greater than overlap capacitance. Therefore, we approximate CGS to be approximately equal to 2/3 Cox W times L, and we disregard the overlap capacitance. However, CGD has only overlap capacitance, it doesn't have the channel capacitance, which means that we cannot neglect that. So this remains C overlap or CGD overlap times W, which essentially means that if W and L increase by a factor alpha, right, then CGS increases by alpha squared and CGD increases by factor alpha, right? Okay, fine. So what is the impact of this? What is the impact of this on a circuit designer's life, right? So let's go back to the very good old common source amplifier and see what is the potential impact, right? So let's go back to the rudimentary circuit that we started off with quite a few weeks back, right? So let's say this is our circuit, right? Okay. So what is the impact of that CGS capacitance? So where will that CGS capacitance come? That CGS capacitance will come here, right? So this will be the CGS. Where will that CGD capacitance come? That CGD capacitance will come here, right? Is there any other capacitance that you can relate to? So let's go back to this structure. Is there any other capacitance that you can relate to? There will be other capacitances, and what capacitances? Note that this is a I think this structure will be better suited to make that point. So let's say this is the P substrate, right? So note that what this drain body junction is reverse bias, right? So what is body? So this is a PN junction here. This is the body is P and the drain contact is N. So it's a PN junction. In order for the transistor to act properly, operate properly, what do you expect that PN junction to be? Do you want it to be forward biased or do you want it to be reverse biased? We obviously want it to be reverse biased because we want all the drain current to flow into the source and not into this PN junction into the body, right? So we want it to be reverse biased. So if you reverse bias a PN junction, what happens? If you reverse bias a PN junction, then again there will be some depletion charges that will get formed, and because they will have depletion charges, essentially it's a diode, reverse bias diode, which means that you will also have some capacitance associated with it. And where will the capacitance come from? That capacitance will be between the drain and the body. Similarly, you will have a capacitance between the source and the body. Correct? So essentially we'll have additional capacitance between drain and the body, and we'll also have a capacitance between the source and the body. And what will this capacitance be proportional to? What will be CD be proportional to? Will it be proportional to the length? Will it increase with the length, or will it increase with the W? Clearly this also will increase with W, right? Because length doesn't really affect CDB, right? So if you increase the size of the transistor by increasing W, CDB increases, right? So CDB is also proportional to W, and CSB is the same thing. It will also be proportional to W, right? So we should also keep that. We should also keep that in mind. Okay. So this is all good. So what is the now clearly you can see that we have more components to deal with, right? So how should we go about analyzing this? So what we will do is so let's split this. Let's use the small signal equivalent of this architecture, right? So what is the small signal equivalent of this architecture? Let's further assume that these sizes of R1, R2, RS, C1 have been adjusted in such a way that they don't load the input, right? We have been doing this forever now. Even if we don't assume that, let's assume that. So what will be the small signal equivalent of this structure? Let's sketch the small signal equivalent of this structure, then we'll make the assumptions. So now the small signal equivalent now changes to, this is Vi, RS, we have C1, then we have this R1 parallel R2, right? So now you have a CGS. CGS between the gate and the source. We have this GM VGS, then we have this RL, but on top of that now we have a drain to made a mistake here, so we'll have a CDB grounded, RL grounded, and probably I should mark these with a different color because these are new elements that we are incorporating. So this becomes the CGS, so this becomes CDB, and this becomes CGD, right? So this is drain, this is source. In case of a common source amplifier, this happens to be ground, right? So since this happens to be ground, all of them get connected. But note that if you are dealing with a common drain amplifier, then it will not be the ground, right? So then you'll have to make adequate, you'll have to account for that. Okay, fine. So I was talking about an approximation. What is the approximation that I was talking about? So the approximation that I was talking about was as follows. So if we are designing a decent common source amplifier, what are we assuming? We are assuming that R1 parallel R2 is not loading the source, C1 is large enough to be treated as short circuit, and so on and so forth, right? If those assumptions are right, so assuming, as a designer, we would like to make a circuit that works, right? So which means that these assumptions have to be right, otherwise you have to go back and change the component values. Assuming C1 is large enough to be treated as a short circuit, and R1 parallel R2 does not, well, I mean, we don't have to assume this. I mean, let's keep this, right? If this is the assumption, then how does our life change? So how does this structure change? So this is RS, this becomes R1 parallel R2, then this becomes CGS. Now CGS can be grounded because our source is grounded. Then we have GM-VGS, we have CDV, right? And we have RL, and we have CGD. So these are the this is how the transistor model now evolves, right? We have neglected channel length modulation because we have RL, right? We can neglect channel modulation. Okay, so if this is the case, then we have to go ahead and analyze this structure once, right? Before we understand what is the impact of adding these capacitances and how it affects our life going forward. Okay, so that is what we will do next.